Hi, I'm John,
Hi, I'm Kamal.
And I'm Matthew.
and welcome to Nuclear Physics 101.
Part 1, Parts of the Atom. The atom consists of nucleus with electrons orbiting around it. Inside the nucleus are protons and neutrons. Protons and neutrons are called nucleons because they are located in the nucleus. Protons have an overall positive charge, and neutrons have an overall neutral charge, while electrons have a negative charge.
Protons, neutrons, and other subatomic particles are made up of things called quarks. There are 6 types of quarks: up, down, strange, charm, top, and bottom. But today we're only going to focus on 2, up and down. An electron, a proton, and a neutron. A neutron has 2 down quarks and 1 up quark. Each down quark has a minus 1/3 charge, while each up quark has a plus 2/3 charge, making for an overall charge of 0. On the other hand, a proton has 2 up quarks and 1 down quark, making for an overall charge with plus 2/3 making 4/3, and then minus 1/3 to get 3/3 or plus 1 charge. An electron is made up of no quarks and is one of the fundamental particles in the universe and cannot be broken down any further. There are 4 fundamental forces in nature: gravity, electromagnetism, the strong force, and the weak force. Right now we're going to talk about the strong force. Here is a proton before and after the strong force goes into effect. Here we have 1 down quark and 2 up quarks on both sides. But what is different is the characteristic of quarks called color. There are red, green, and blue quarks, and quarks are constantly changing colors through the strong force. This particle right here is called a gluon. Gluons go from one quark to another, yanking both of them together and keeping them inside the proton. Here, the gluon goes from the green up quark to the blue down quark and creates a green down quark and a blue up quark, thus changing the color. Not only does the strong force hold quarks together inside protons and neutrons, but it also holds the nucleus together by exchanging gluons between the quarks of protons and neutrons inside the nucleus.
Hi guys, so today we're going to be talking about the 2 nuclear reactions, fission and fusion. So we're going to start with fission first. Now fission is basically the splitting of the nucleus, one nucleus into 2, as animated up here. And fusion is basically the opposite. It is the coming together of 2 nucleus into 1. So let's get started. Again, fission is the splitting of the nucleus. And then in our society where we have to generate a lot of energy basically for power and electricity, we basically use uranium, the element uranium-235, because it is very commonly used for fission, and it's easier to break down than others because it's obviously massive 235. And then what happens is with the fission reaction, since you are splitting a nucleus, you are also giving off energy because you have to conserve energy at the same time, and that is the energy emitted. Now the thing with the energy emitted is that you can, when the energy is emitted, like for example in an atom bomb, when the atom bomb explodes, it emits not only an immense amount of heat, but it emits gamma rays, and beta rays, and X rays, all kinds of rays, and that can do a lot of damage to you. Hopefully you're not in the middle of it. And then that's basically why fission is used in nuclear warheads and nuclear reactors like this one up here. So the way it works in nuclear reactors is the fission reaction that occurs within the rods emits heat, and then that heat is turned into steam, and then the steam drives a turbine which generates electricity. So that's the way fission works. But then yet again, there's drawbacks to using fission, because with fission, if you say you have uranium-235, you have an atom, and you shoot a neutron. The neutron is the atom's going to split, but it's going to keep on splitting. So it's not going to be contained. And then we can see that in atom bombs, because when you see an atom bomb explode, you see a flash of light, and then a ginormous mushroom cloud, and then debris everywhere, and then waves. And the thing with the nuclear bomb is that that's an example of an uncontained fission reaction. Now, the reaction that goes on in an atom bomb is highly similar to the reaction in a nuclear reactor, except that the reaction in a nuclear reactor is contained. The water contains the water. If you look at a picture of a nuclear reactor or the uranium rods in it, they are sitting in water, which basically cools and slows down the reaction as well, so that it doesn't become unstable and turn into a nuclear reaction. Alright guys, so now we're going to discuss fusion. I mean, there's not much to say about fusion, so I'm just going to talk about it briefly, because I mean, we don't use fusion because it's a lot more dangerous than fission reactions, so we don't know more about it, so there isn't much to say. So anyways, fusion is the fusing of two nuclei into one, and we don't conduct fusion reactions because not only are they difficult to initiate, like for example with fission, we had a neutron being shot at uranium-235 atom, and that was the initiation. We have the technology to initiate that, but initiating a fusion reaction is much more difficult and it's a lot more dangerous, because number two, fusion reactions are technically 4 times more dangerous than the fission reaction. And in a sense that's good, because that releases a lot of energy that we can use in our society, but it's dangerous because we can't tame that energy, and the energy might be so strong that it could kill us in the process of making it. And then third, fusion occurs mainly in space. It's basically fueling the stars. It's basically fuel for the stars. So basically when you see the sun up there, you are basically witnessing fusion reactions, like a lot of fusion reactions. And then again, fusion just occurs within stars and suns.
Today we're going to be talking about alpha decay. Alpha decay is when you have a radioactive isotope such as uranium-235 emit an alpha particle. An alpha particle is just a helium atom with 2 protons and 2 neutrons to make a total atomic mass of 4. When uranium emits the 2 protons, its atomic number drops from 92 to 90, and it changes elements from uranium to thorium. Thorium also has an atomic mass of 4 less than the atomic mass of the original isotope, in order to make up for the 4 atomic mass units that went to helium. The reason radioactive isotopes do this is to become more stable. The reason isotopes undergo alpha decay is to become more stable. Only large isotopes, such as isotopes of atoms larger than the element lead, which is the 84th element, can undergo alpha decay. All other elements can only undergo beta and gamma decay, which we will talk about soon. Today we're going to be talking about beta decay. Beta decay is when a neutron interacts with a neutrino to form a proton. The way it works is a neutron consisting of 2 down quarks and 1 up quark interacts with a neutrino, which breaks into a positive W boson and an electron. The electron goes flying off into space, while the W positive boson interacts with the slightly negative down quark to form an up quark in the proton. The new particle now has 2 ups and 1 down instead of 2 downs and 1 up. Therefore, it is now not a neutron, but a proton. Now we're going to be talking about gamma decay. Gamma decay is when a gamma particle is emitted simultaneously when a alpha particle or a beta particle is emitted during alpha or beta decay. The purpose of gamma decay is to release the extra energy that was required to hold the former large nucleus. At the CERN Super Collider, what they do is they take 2 elementary particles, in this case a proton and a neutron, and sling them around a large ring until they collide at a certain point. At that point, the two particles collide with such momentum and such force that their quarks, the particles that make up protons and neutrons, can sometimes form in new combinations and make new particles that aren't protons or neutrons, such as the Higgs boson and many other types of particles. Using our knowledge of nuclear physics, we can also create new elements, such as flerovium and livermorium. The way livermorium was created was they took curium with 96 protons and smashed it together with calcium with 20 protons to make a grand total of 116 protons for livermorium, a new element. Livermorium then immediately went through alpha decay and decayed into flerovium, element 114.